Exercise 41.6. This exercise is to be solved with the assistance of the TI-Nspire CX CAS version 3.2. Consider the region bounded by the graphs of y equals x cubed minus 5x squared minus 18x plus 72 and y equal 2x cubed minus 6x squared minus 50x plus 62. Part A. Provide a graph of the region. Part B. Provide a graphic approximation of the area of the region. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Part D. Assess the correctness of parts B and C by examining for a consistency between the two results. Part E. If able, obtain an exact value for the area of the region. Part A. Provide a graph of the region. Okay, for starters, I like the first page to be a summary of the solution, and then all the other pages can be supporting documents for the summary. So here, click on Menu and decide to add notes for page 1. And first, a title to what we have going on here. I'll say this is Exercise 41.6, Solution Summary. Part A, I will point out that a graph of the region is on page 2. Okay, now since actually this here is pretty much a title, I think it needs to be bolder. So let's go ahead here and format the text. Click on B for bold. I will even try for a larger font if I can get it to fit without wrapping to a second line. That's too much. Okay, 12 point is fine. Close that. And I would also like to center this in the page a bit. Okay, one more preliminary. I'd like to see what calculation mode the Nspire is in right now, and I also want to set up the number of digits displayed in a calculator or a math box. And for that, we go here to Document and Settings and Status, Document Settings. Alright, noting that in Part C there is a 5 significant digit request for a decimal answer, so just making that so that it happens automatically. Go to Float 5. And then the second issue is the calculation mode. Right now it's in auto. What's auto mean? Auto means that the calculator will provide an exact solution as long as there are not decimal number inputs, and as long as the exact solution is concise. Alright, so auto is quite good. Keep that and click OK. Time to get that page 2 going, so that's Control Add Page, and this will be a Graphs application. The enter line opens, and with these two functions here, it is apparent that both cubic functions with positive ax cubed terms. Okay, so I can already anticipate one of two shapes. In each case, one would be that cubic curve having only an inflection point, no relative extrema. A second possibility is a cubic curve that has an inflection point and a pair of relative extrema. It's kind of helpful to do a little bit of anticipation before you start putting things here, because this will help in determining how much zooming out we need to do before we feel that we have captured the bounded region rather than omitted something. Okay, so let's proceed here. F1 of x, use the first y, and that is a matter of recording and enter. Okay, looks like one of those cubic curves having a pair of relative extrema. Hitting tab, put the second equation into F2 of x. Here we go. Okay, Looks like a second cubic function having a pair of relative extrema. Now, having said that, this means that the x-axis already is plenty large. In fact, I will even kind of expand this graph like so. What I'm trying to do is I want to get the bounded region filling much of the visible coordinate system, and I also want to leave room for all labeling so that the labels are not in the way of the bounded region at the same time. Okay, so now that I've done this and I realize these cubic functions, it would be a pretty efficient thing here to go ahead and use the zoom fit. Zoom fit leaves the x-axis untouched and changes the y-axis so that all of the points will appear. Again, just the y-axis getting changed. So zoom fit, try that. Okay, this just about shows us what is going to be bounded here. The bounded region is kind of a two-part region, and I think just moving this over a little bit for starters. Now I can get this, I think, a little larger and still have room for labels. So for this, I will go to the menu window and zoom box. Zoom box I like it. It gives a lot of control over exactly what you get for the result. And I want to get that intersection point. So I'll say there for first corner. I need to get the second intersection point and the region that's bounded. And I want some room for labeling too. So maybe I'll go up kind of high here to put labels in the upper section, so enter there. Alright, this might be just about what I want right now. I'm going to escape that tool, move this over a little bit. Okay, start making these labels located in better positions. Okay, and then this F1 being near the blue graph would be pretty good. Okay, now something else that looks a little clumsy, I think, right now, and that is these coordinates, these axes rather. We've got scaling numbers like here, negative 146.75 and 176.81. Okay, I like things to look simpler and cleaner, so I'll now go ahead and change that a bit. So menu, Windows Zoom, Windows Settings. Okay, X min, let's say negative 6, tab, X max. Right now it's at 7, okay, make it an 8, and tab. The x-axis right now is 14 units long. I usually divide by 10 to get an idea of what will look okay, and that would be 1.4, so I'll call it 2 and hit OK. The Y min, okay, I'll say negative 150, tab. Y max, 170, okay, we'll call that 175. Okay. Alright, right now, this y-axis is, 325 units long. Scaling every 25, maybe that will be okay. Okay, I think that looks cleaner, nicer. I'll keep this. Let's see, what else do we need? Those intersection points are very important to a problem like this, so I think those deserve to be on the graph. Before I do that, though, I don't want to see 10 significant digits for all these coordinates. That would look very clumsy. So I want to keep this graph as simple and informative as possible. So I will set the settings. Now, although I'm tempted to say float 2 for these coordinates here, I am also anticipating an area that gets recorded in this graph application, and with this y-axis being going down to minus 150 and so on. These areas just have just appear to be in the hundreds type numbers, so I think I will actually float 3 digits for the graph application. And to do that, going to go to menu and settings. Now we see we have a graphs and geometry settings, not a document settings. So this affects the graph, and display digits, change that to 3. Okay. Alright, now here's our chance to go ahead and get those intersection points. Menu and geometry, points and lines, intersection points. Okay, you have to select your 2 graphs that you intend to intersect. Here we just have our graph 1, enter, and go over here to graph 2 and enter there. Okay, so these points are okay, fine. I'm going to hit the escape key, and now let me move these to locations that are not in the way of the region itself. Now, the region, want this to be clear with shading, and I find that using a polygon is a pretty good method for this. So, menu, geometry, shapes, polygon. And a second polygon to get the other portion of the region. Okay, put this tool away. Now for the shading, it's a matter of going to the polygon, context menu, color, fill color. I'll choose yellow. And this polygon as well, same thing. Okay, now I do want to clean this up further for the part A, graph of the bounded region. However, I want to use these polygons as a source of graphic approximation, part B. So I'm going to keep a copy of this right here for future part B. I'll do that by going to Control, Show Document Pages, and then I can copy and paste this page here. And now here's my page 2, so this will now go on to become a graph of the bounded region. Alright, so how can we clean this up? We don't want these black line polygons running throughout, so first thing I can do is go to the polygon and shade its lines that same yellow color. Okay, that's better. Now I need to get rid of all those polygon vertices, keeping only the points of intersection. So that's a matter of successfully going to the point, context menu, and hide. And just keep doing that. Alright, almost there. Just one more thing, and that is I need to provide a labeling of the fact that this yellow shaded is the bounded region. So a little bit of text here. Okay, and I think that will do it for part A. Part B. Provide a graphic approximation of the area of the region. For part B, I'm going to go to page 3 and finish that up. Okay, here we have these pair of polygons that can be used to approximate the region. We just need to get the area here, so that's no problem. So select the polygon, go for a measurement area. Okay, and put that right there. This polygon also needed its area. Okay, move that there, and now we could make a statement here. We need to add these two together. So let's see, 3 and 3 is 6, 5, 3, 6. And that is what we want to sort of say here as a summary statement of this. So a little bit of text. Okay, and I think I'd also like to record this on the summary page as well, that 536 square units part. So let's go to our summary page, and here in part B, by using a pair of polygons to approximate the region, we find that the approximate area is 536 square units. And we could say see page 3. Okay. Part C. Provide a calculus calculation which yields a decimal approximation, 5 significant digits, of the area of the region. Using calculus to calculate the area of a region means slicing up the region and then summing the areas of the slices. Let's start by trying out some thin vertical rectangle slices and see what we think. Next, we want to try to formulate the area of a slice. Okay, they're rectangles, so that should be length times width. And since they're sitting in this coordinate system, the length would be the upper y-coordinate minus the lower y-coordinate. But actually, that presents a bit of a problem, because watch the tops of the rectangles as we go across. Things change. The tops of the rectangles are initially defined by the red curve, but then change to become defined by the blue graph. The bottoms of the rectangles, a similar situation. They start off defined by the blue graph, but change to be defined by the red graph. So apparently we have two types of thin vertical rectangles. The ones on the left have a length equal to the red graph y-coordinate minus the blue graph y-coordinate, algebraically, f2 of x minus f1 of x. On the right-hand side, the thin vertical rectangles have an area where the length is the blue graph y-coordinate minus the red graph y-coordinate, algebraically, f1 of x minus f2 of x. We could do this sort of thing, but it does require two definite integrals to accomplish it. Actually, there is a single formulation that can be used to describe the length of all these rectangles, and that would be to say that it is always the absolute value of the difference of their y-coordinates. Okay, let's try that. Much better. Now, as far as the width of the rectangles go, it's always a little piece of the x-axis, and thus formulated as dx. Alright, so let's take the ideas of our visualization and put them into formulation here. So see, on the document, we could say that a calculus solution can be obtained by using a definite integral which sums thin vertical rectangles. We should point out where we've got the limits of integration, and we do need to do that, but we will say our plan here, and that is that the limits of integration have been stored in variables a1a and c1a. So let's go do that. Now that means we go back to the graph here, and let's take this first coordinate here, context menu, and store. Okay, now because it's a left hand limit of integration, A is a popular letter, but A1, because the Nspire suggests not using single letters for any of your variables, so we'll do that. And then I'm going to suffix it with a 1 because it's a, well, a decimal approximation in this case. Since we have a display digits of 3 and we only see a -5, that's actually exact, but okay, just to be consistent with everything, I'll still label A1A and enter. And this X coordinate here, I also may need this in the future, so I will go ahead and store this one as well. Okay, so left to right A, I'll make this one B, B1, A, because it's a decimal approximation right here, and enter. And this one, same idea, store it, and this will be C1A, enter. Okay, now that we've got those stored away, we can go back and proceed to do the calculation now. So we would have area equal to, okay, let's go to the menu, calculations, calculus, integral. Okay, lower limit, that's A1A, tab, upper limit, C1A, tab. Alright, the integrand is to be the, we found to be the absolute value of f1 of x minus f2 of x dx, go. Okay, got a number here. We have 5 significant digits there, and just to clean this up a little bit, I like that little triangle there to be at least an approximate equals to sign. So back here, here, and there. Okay, good. And I'll put here square units to sort of finish it off. Okay, there's our part C. Part D. Assess the correctness of parts B and C by examining for consistency between the two results. Let's look back at what that graphic approximation was. 536 square units. Okay, let's note that again here. I'll just use the number for this comparison here. And the calculus calculation, okay, was about 543. This is really good news. Alright, so I always use a larger number for these. About 10% would be 54 units. And these are, well, from 36 to 43, that's only 7 units difference there about. So 54 is 10%, so 5.4 would be about 1%. And so we're not exaggerating by saying these two results are within 2% of each other. And that would be consistent. And that allows us to then go ahead and conclude that the solutions to parts B and C are very likely correct. Okay. Part E. If able, obtain an exact value for the area of the region. Okay, the first stage is going to be to get the limits of integration exact. And let's see, we'll do this on another page. I don't want to have I don't want the summary page to have too much detailed calculations, so let's push this off onto a calculator application, page 4. Now let's go do that and see if we can be successful. So here it's a matter of control add page. Okay, the calculator application. Alright, we need to try solving f1 of x equals f2 of x and hope for exact results. Let's see if we can do that. Okay, we got exact results. Very nice. Now let's go ahead and let's just store all three while we're at this. So for instance, we can come up here and you probably don't need to do a copy and paste, but since I'm doing the same thing repetitively, I will. So here, select it and then paste it here, and then we can go Control Store to. Okay, this will be A1. That's exact, so I'm not going to suffix it with an A anymore. That's going to be the actual A1, and enter. Let's go up here, shift arrow over to select this number. And by the way, when it does a solve like this, the results are given to us in ascending order, so that's why I know this goes A1, B1, C1 respectively. Okay, now that's selected, enter, paste it on a new line down here, and then it's just a matter of going Control Store to B1, and now the third number here, shifting, got that number, selected, enter to paste it here, and Control Store to C1. Okay, we did that, and we should probably go to the summary page and point that out. Okay, now here's something probably just going to point out. You might think that we can just redo our integral of part B, that is this one here, and we could just put in our A1 and C1, but it won't be exact. And the reason is that having these absolute values in the integrand causes the calculator to shift back over to decimal approximations instead of exact calculations, which you can confirm for yourself if you like, and be a little bit disappointed that it didn't just provide an exact answer as is. Alright, so now this means we need to not use absolute values in our integrand, which means we are going to now require a sum of two integrals to get the area. How shall we do that? Let's look back at our graph of this region. Now in the left-hand portion, if we sketch in one of our thin vertical rectangles, we can see that the height of the rectangle is the y-coordinate of the red graph minus the y-coordinate of the blue graph. Or algebraically, that would be f2 of x minus f1 of x. The width, as usual, is dx. Next, let's pan over to the right and dimension a thin vertical rectangle for the right region. We find that its height is a y-coordinate of the blue graph minus a y-coordinate on the red graph. Algebraically, that would be an f1 of x minus an f2 of x. And meanwhile, the width of the rectangle is, of course, dx. We could explain to the person reading our solution what the situation is. Alright, time for a math box. Calculations. Calculus. Integral. Okay, the first one. A1 to B1. We looked at the graph there and decided the height of the vertical rectangle is f2 of x minus f1 of x. Dx plus, okay, need another integral, menu, calculations, calculus, integral. Okay, now this one goes from B1 to C1. And now we need to use f1 of x minus f2 of x dx. Alright, let's see if this will work. Enter. Okay, got something here that is exact. Alright, let's fix this up to have that little triangle be an equals sign. We could maybe add on the square units. Thus, an exact area is obtained. And we probably should put to rest the idea that, is this different than the decimal approximation? Okay, that would be a problem. So this number here, which isn't too obvious by inspection, let's go ahead and copy it. Paste it down here. And now let's go to the menu, and for an action, let's have this approximated. Okay, very good. Oh, and let me point out here what we were going to do. For peace of mind, we note that, and let's make this an about equals to, which is consistent with the calculation of part C. Okay, great, done.